The very concept of laws of science presents a challenge to some who would seek to explain everything naturalistically. They understand that this has the implication of a lawgiver, and they seek desperately to avoid that. And so how do they explain laws of science? I think this conflict, this challenge, is revealed in the statement by James H. Shea, who's editor of the Journal of Geological Education, writing in geology. He says the concept, that is, of laws, is anachronistic in that it originated at a time when the Almighty was thought to have established the laws of nature and to have decreed that nature must obey them. It's a great pity, he says, for the philosophy of science that the word law was ever introduced. And can you imagine a scientist saying it's a pity that anybody ever talked about the laws of science? Science is discovering the laws, and science originated when, in this period when they thought the Almighty had decreed these laws, they decided no longer does superstition or happenstance govern what goes on, but we can discover laws and we can repeat, and we can see this demonstrated. And in that context of believing that the Almighty decreed the laws, we had men like Kepler and Newton who said science was thinking God's thoughts after him. We see the development of science. It couldn't develop until they got that concept. But now then they're moving away from that concept because they are dedicated to their naturalistic philosophy, and they see this would imply a lawgiver, and they want to avoid that at all cost. And so they, of all things, say it's a great pity for the philosophy of science that the word law was ever introduced. Well, there are laws. Whether we want to use that, or anyone wants to use that term or not, I certainly have no problem with it. And I think true scientists would have difficulty finding any other term that would describe it. Albert Einstein is certainly considered one of the leading scientists in the history of science. And he's talking about the laws of thermodynamics. We'll be focusing on those laws, particularly in this lesson. But he says regarding classical thermodynamics that this is the only theory of universal content concerning which I'm convinced that within the framework of applicability of its basic concepts, it will never be overthrown. Now, that's a very strong statement, and scientists are very guarded against these flat-footed, dogmatic statements of this nature. But here is the concepts, or the laws, he would call it, in which he has the greatest confidence. This is, we talked in a previous lesson about what it took to be established as proof scientifically. Of course, always tentative, but proof as the scientist uses the term. And these concepts meet all of the criteria. We can observe it, we can test. And it has been tested and observed for a long time, and he says he is convinced it'll never be overthrown. The first law of thermodynamics is sometimes called the law of conservation. We're told that matter, energy, can be interchanged, but neither can be created or destroyed. Now, basically, what's being said here is you can't get something for nothing. Now, that's not a new concept, and you might not have thought of it as a law of thermodynamics. That terminology may scare some people, but it's a concept with which we are all familiar. You can't create something out of nothing, nor can you completely eliminate the matter or energy. Something always exists before and after any exchange that we see today. That's the first law of thermodynamics. Isaac Asimov, who has recently gone on to a clear elimination, someone said, by this astronomer and physicist, he has passed away. But he says this law is considered the most powerful and most fundamental generalization about the universe that scientists have ever been able to make. Now, he was an atheist, or certainly a militant agnostic, if you can imagine that. But he acknowledges that this is a law, and it is the most powerful, most fundamental generalization any scientist has made. Now, this is certainly a true law. And then he says no one knows why energy is conserved. Well, maybe he should leave that lack of information to himself. I think we have an adequate explanation, though he obviously does not. But he says in all that anyone can say, and over a quarter of a century and a quarter of careful measurement, scientists have never been able to point to a definite violation of energy conservation. Now, this involves experimentation. This involves repeatability. This involves exactly what science is about. And with all of this testing and all of this observation, there's never been a violation. He says that's true either in the familiar everyday surroundings about us, or in the heavens above, or in the atoms within. Now, that's a very broad scope. And he said there's never been a violation in any of these areas. But the concept of uniformity that says everything that we see in this universe came into existence as a result of the present laws that we see now would tend to indicate we get something from nothing somehow. If all things came into being as a result of present laws, and the present laws say you can't get anything into being from nothing, then there's some obvious problem here. But this, of course, is the theory. I don't think you can get what we have by natural processes. But Asimov tries to deal with this. He says, perhaps in an infinite sea of nothingness, if you can imagine that, He says globs of positive and negative energy. Now, wait a minute. I thought he said nothingness. Well, anyway, let's see what he's got to say. In this infinite sea of nothingness, globs of positive and negative energy in equal-sized pairs are constantly forming. Now, you see, the first law says you can't do that. But he says perhaps, so maybe that's the way you get past this most fundamental generalization of science has ever been able to make. But these things are forming from nothing, and after passing through evolutionary changes, combining once more and vanishing. And we're in one of these globs in the period of time between nothing, and wondering about it. Now, this is supposed to be science. You've got things forming, and you've got certainly things that have been formed, but it's in a period of time between nothing, and we came out of nothing. But that first law says precisely the opposite of what he's saying, and he's the one that said this is the most fundamental generalization that scientists have ever been able to make. He is also a good science fiction writer, by the way. Here we have the law of conservation, a fundamental, powerful generalization. Even Einstein says he's more convinced about this one, that it'll never be overthrown than any other. And this principle of uniformity that says from nothing we get everything, that all things came into existence as a result of present laws, we have an obvious problem. Now, one is a law that has been confirmed scientifically. The other is a theory, and I think I know which one ought to give if you're going to be a good scientist. They are certainly in conflict with one another. Now, the second law of thermodynamics is likewise confirmed by empirical observation. It's described sometimes as the principle of entropy increase. I think it's said that way to confuse people. Well, not really, but it does. It's something increasing. No, entropy is the measure of disorder, and so the disorder is increasing. And so, in effect, it's saying things go downhill and tend toward disorganization. Now, you probably didn't call it entropy increase or the second law of thermodynamics, but you see it and are very familiar with it. This is not news to anybody. We're familiar with it every day. But let's think of these models in terms of this second law, and notice what Isaac Asimov, again, has to say about it. Now, Isaac Asimov has written probably more books than anybody around today. Someone said he's probably written more books than he's read, which I doubt, but a very prolific science writer and an acknowledged expert by a great many people. Writing in the Smithsonian Institution Journal, says another way of stating the second law, then, is the universe is constantly getting more disorderly. Viewed that way, we can see the second law all about us. Now, we understand things getting more disorderly. This is not new. He continues describing it. He says we have to work hard to straighten a room, but left to itself, it becomes a mess again, very quickly, very easily. Did anybody know that? Is this news to anybody? No. Even if we never enter it, it becomes dusty and musty. How difficult to maintain houses and machinery and our own bodies in perfect working order. How easy to let them deteriorate. Again, this is not news. This is something we all understand, and this is what we're talking about. He says, in fact, all we have to do is nothing, and everything deteriorates, collapses, breaks down, wears out all by itself, and that is what the second law is all about. Now, if we define the creation model by Scripture, we would predict that this would be a principle that would pervade the universe as a curse, as a consequence for sin. Now, this is not a scientific conclusion, but is a definition of the model which we can then investigate scientifically, and what we see in science certainly confirms that. Things do deteriorate. They degenerate back to dust, as would be predicted by what we read in Scripture, and we see scientific confirmation of that. But, of course, the evolutionist would predict the opposite. The second law of thermodynamics says there is a loss of order in all real changes. But the principle of evolution is the idea that everything is a directional process going upward, and we're told the whole universe is evolving upward, giving rise to an increase, and that's the way it's defined. This, of course, is the theory, and notice the way it's expressed here by Weisskopf, who's head of the Department of Physics at MIT, writing an American scientist. He says, the evolutionary history of the world, from the Big Bang to the present universe, is a series of gradual steps from the simple to the complicated, from the unordered to the organized. Now, you see which direction this is not, as the second law of thermodynamics would indicate, degenerating, entropy increase, disorder increase, but just exactly the opposite. From the simple to the complicated, from the unorganized to the organized, from the formless gas of elementary particles to the morphic atoms and molecules, and further to the still more structured liquids and solids, and finally to the sophisticated living organisms. To remind us of the statement by Harlow Shapley, who's talking about origins when he says, in the beginning, hydrogen. Asked where the hydrogen came from, he says, I beg to be excused from that problem. In fact, he defined hydrogen as a colorless, odorless gas which, given enough time, would evolve into people. And this is supposed to be science. We know what happens to gas. It dissipates, doesn't it? There are strong dissipative forces that we can measure. Yes, there are attractive forces of gravity, but the dissipative forces are much stronger, which is why you turn it loose in the room, it spreads out. When you see the the smoke coming out of the campfire. It doesn't get more organized by gravity. It spreads out, doesn't it? That's one of the laws of physics we can easily test and measure. But he says everything is getting more organized and more complex and just begins with this formless gas and winds up as people. Now, that's an upward process, and that's different from the downward process. That's obviously different. Evolution says everything gives rise to increase, whereas the principle of entropy increase, the law, the second law of thermodynamics, tells us that things go downhill. And while one's a theory and the other is a law, I think we ought to understand which one prevails. Well, we understand the world, in spite of evolutionary theory, is running downhill. The universe is, in spite of what we're told and what faith would predict of the evolutionist. But there's an answer that is typically given to the obvious implications of this second law, and we want to consider that. We're told, oh, there is an open system, and that this only applies to open systems. I think that's a vacuous answer, but nevertheless, that's what we always hear. And it is true, certainly, that we can make things go uphill. You can make water run uphill, can't you? By using a pump, having energy. Of course, it was designed by intelligence, but you can impose extra energy on a system and information, like the DNA within the acorn, and cause the tree with a lot of extra energy and a lot of information to go uphill, which, of course, eventually is subject to the principle of decay and degeneration, as is the water pump. But nevertheless, we can see temporary evasions of the prevailing process by imposing extra energy. And we're told the Earth is open to the energy of the sun, and so all of this extra energy bathing the Earth can drive the process of evolution and cause it to go upward. Now, extra energy is an essential part of any upward process, but it's not an adequate explanation. It takes more than just the expenditure of energy. But regarding the open system idea, notice the statement by John Ross of Harvard in Chemical Engineering News. He says ordinarily the second law is stated for isolated systems. You have to make the equations work. But he says the second law applies equally well to open systems, and of course all systems are to some degree open, and what we see in the living world certainly are open systems. Our experience relates to that. Arnold Sommerfeld, in his book Thermodynamics and Statistical Mechanics, says the quantity of entropy generated locally cannot be negative. In other words, the disorder has to increase, irrespective of whether the system is isolated or not. So if somebody says it doesn't work in an open system, they just don't know what they're talking about. We can impose extra energy, which is essential but not adequate to explain an upward increase. Notice the statement by George Gaylord Simpson, a very famous evolutionist from Harvard, and W.S. Beck in their textbook. The simple expenditure of energy is not sufficient to develop and maintain order. And then they give a very graphic and obvious illustration. A bull in a china shop performed work, but he neither creates nor maintains organization. Now, these are devout evolutionists. But energy is necessary, but not sufficient in order to produce upward organization. He says the work needed is particular work. It must follow specifications. It requires information on how to proceed. And this is the real key. And if we think of these processes in terms of information, I think we'll have a handle on the real problem that the evolutionist has in making this go uphill. Information, like the physical systems, like living systems, does not go uphill by itself. Information, like the physical systems, degenerate, and it goes downhill. Now, you have to continually update. You have to continually revise and correct. And informational thermodynamics uses the same kind of equations as the physical thermodynamics. We see the same processes involved. Now, Carl Sagan is talking about the information content of the simple cell in the Encyclopedia Britannica, when he says the information content has been estimated at around 10 to the 12 bits. Now, if you're a computer expert, you may understand that. That's an awful lot of information. But he says it's comparable to about 100 million pages of the Encyclopedia Britannica. Now, if you find the Encyclopedia Britannica laying out on the beach, washing up, you don't just say, well, look what just happened to form by washing around in the ocean. Here's information that doesn't get there by itself. What happens is it degenerates, and information, if anything, goes, when it changes, goes downhill. Now, how do you get this originally? That's what you have to have the simple cell. Where did the information come from? 100 million pages of the Encyclopedia Britannica. Well, Bill Gates, as we pointed out earlier, says the DNA is like a computer program far, far more advanced than any software. Where did this come from? He would tell you his software program didn't form itself. That information didn't get uphill on its own. It had to have intelligence to guide it. And here is more information than any program he's got. How did you get it uphill to start with? And you have to have it to start with. Well, we're told the answer is the sun shines on the earth. Well, now that explains the source of energy. But it does not explain the source of information. Those are two different things. And no matter how much energy you have, you can't get the information the 100 million pages of the Encyclopedia Britannica to form the simplest cell. And continually I ask this question on the college campuses. Yes, you can show that necessary element of energy and show a source for it. But that's not an adequate explanation for any increasing system. You also have to have an increase in information, and with the simplest cell you have a tremendous amount. My question is not where the energy came from, but where did the information come from? And you know the answer that I get to that question? You're listening to it. It's silence. You don't have an answer to that question. They don't have an answer. There is an obvious answer. I mean, it's just like trying to ignore an elephant in a room. The answer is obvious of where the information came from. It had to be from a non-natural source. If you want to call it supernatural, you can. But it did not come by natural processes, which says things go downhill. You don't get it uphill by itself by natural processes. And so saying, well, we've got energy from the sun, certainly by no means answers the problem. We see the implications of the second law of thermodynamics all around us, everywhere we look. And I'm not sure everything that we look at that's degenerating necessarily as a result of the second law, but we're told everything goes uphill, and I think it is significant in relation to that concept. Stephen Gould is talking in his book Wonderful Life about what we see in the living world, certainly indicated by the fossil record. He said we see the sweep of anatomical diversity reached a maximum. Now, the prediction of the fossil record, as we'll see when we look in a later lesson, is that you have a simple, gradual, slow beginning. But no, he says it was most diverse at the beginning, and that diversity has degenerated. The sweep was a maximum right after the initial diversification of multicellular animals. The later history of life proceeded by elimination. It has degenerated. We've lost diversity. It was a maximum at the start. It is not expansion, which the evolutionist would predict. We see this downhill process illustrated in the fossil record in the living world. Elimination, not expansion. Interestingly, he in Nature was talking not long ago, 97, about the law, as I was taught, Cope's law, that says all bodies tend to increase. Now this is, of course, the evolutionary philosophy, and you look in the books and you see these graduated man charts and graduated horse charts. Everything's getting bigger and bigger, and this is supposed to be proof. And Cope said this is a law all the way back in 1871, that body size of organisms in a particular evolutionary lineage tends to increase. But Gould acknowledges in this introductory article in Nature that Cope's rule has failed a most comprehensive test applied to it yet. And there followed this comprehensive test, very detailed, elaborate, scientific investigation of the law, and as Gould acknowledges, hey, it fell flat on its face. It does not work, and so it's not a law. It shouldn't have been called a law in the first place. It was an assumption that was called a law that has now been falsified. But the idea that most people have is that, yes, things get bigger over time. But when you look in the fossil record, that's not the case. Notice the statement in the text Geology by von England and Castor, referring to the Pliocene, but you can see similar statements about all of the periods. He says that mammalian life, and of course we like to think about mammals that we belong to, it was richer in kinds of larger sizes. There were more of them, they were bigger, had a more abundant expression in the Pliocene than in later times. It went downhill, not uphill, and we can see all kinds of examples of this. Notice in Time magazine, reporting on Leakey's work over in Africa. He's been scouring the gorge, the Avois Gorge there in Africa since 1931, they say. Over the years, he's unearthed the bones of an ancient pig as big as a rhino. Now, I've seen lots of pigs, but I don't think I've seen one that big. But that's the way they are in the fossil record. A 6-foot-tall sheep, a 12-foot-tall bird, and the flat-topped skull of the erect nutcracker man, which I think was a giant gibbon or ape. But this is the way things are in the fossil record, as acknowledged even by Leakey. He's supposed to be a champion of evolution. Not really, as we'll see later. Here we see the picture of a fossil pig. That is the one on the right, is the fossil pig, with myself standing beside it. This is in the Dakota School of Mines. That's the way the fossil record depicts them. But if the pigs were as big as rhinos, how big was the rhino? Well, there he is. This one's from India, almost 20 feet tall. That's the way it was in the fossil record. In the article from Time magazine, they illustrate with this fossil ram that Leakey has discovered. And here Lewis is looking at this giant compared with the modern ram in the background. I can almost be glad that they're not still around. That'd be kind of dangerous, wouldn't it? But they haven't evolved a whole lot in terms of size. Now, often when we point this out, I'm told, well, size doesn't necessarily indicate evolutionary progress. But what are they trying to say then in the textbooks when they show the graduated man charts and when they show the graduated horse charts? They are trying to say, here's the proof of evolution, and that's very influential in thinking. That's the idea. And that idea is false. It goes downhill, not uphill, and that's ending. Now, sometimes we're so told, well, but that's not true with human beings. We have gotten bigger. And obviously we have in the last 50 years, There's been a dramatic spurt, almost 6 inches in the last 50 years on the average. But you go back beyond that, and we see an opposite trend. And most would attribute this spurt in the last 50 years to an increase in the knowledge of nutrition. We know about vitamins. We know about proteins and carbohydrates and the balance that we ought to maintain. And that makes a big difference in the way things grow. 6 inches in 50 years is not the evolutionary kind of change the evolutionist is looking for. If you extrapolate backward, then you would find 100 years ago we ought to have been a foot shorter, and 200 years ago 2 feet shorter, and 1,000 years ago we're minus several feet there. This is much too fast for the evolutionary type of change. When we look at the fossil record, we see opposite indications. Looking, for example, at the Turkana boy that was found over in Africa by Richard Leakey, we see what is now described as a 9-year-old boy that was 5'6". Now, 5'6", we've got populations on the earth that are on the average not that tall, but this is from a 9-year-old boy. And notice the comment that was made in National Geographic by Richard Leakey. The boy from Turkana was surprisingly large compared with modern boys his age. And this statement was made when they thought he was 11. They've learned now that he was 9. He could well have grown to 6 feet, and if you begin with this 5'6" height at 9 years, he'd go taller than that would be the implication. He would probably go unnoticed in a crowd today. And he says this find combines with previous discoveries of Homo erectus to contradict the long-held idea that humans have grown larger over the millennium. Now, you don't notice him in the crowd. He's bigger than modern people, but he's Homo erectus. Why? Well, because you got him back millions of years ago. That's another story that we'll talk about later in the series. But notice his statement that a lot of you have seen in the textbooks that the idea that man's grown larger has been contradicted. Did you know that? Well, that's what's indicated by the evidence, as he acknowledges, but they're not going to tell you that. They tell you the opposite. Everything's getting bigger and better all the time. No, not when you look at the fossil record. We've got a number of fossils, 2 from Italy, over 8 feet, several from the western United States, over 7 feet. We do see some populations that are smaller, just as we do in the live population in the earth today in some fields. We excavated a large ass or donkey from near Lubbock that was 9 feet tall at the shoulder. I don't see we see a whole lot of those in the textbooks. In fact, that'd sure mess up those little graduated horse charts, wouldn't you? Put a 9-foot donkey in there, and you in the fossil record, and you get really a disordered indication. We excavated a bison with a 12-foot horn span. We don't see that. 12 feet. That's huge. And then this is a picture right out of the geology textbook, the extinct glyptodon. They call it that because that's in the fossil record. But he says it's like a present-day armadillo shown to scale down there in the lower right-hand corner. Obviously, he was much, much bigger, 9 times larger in the past. I think that would probably flatten some pickups instead of the other way around that we see often down in Texas. Looking here at the fossil of a turtle that looks identical to modern turtles, at least to the average eye. The expert can tell a few minor differences, but you have to be a real expert to see them, except if you're there in person and you notice the size. This is over 14 feet from the tip of his nose to the tip of his tail. That is a huge turtle. That was from the Big Bend down in Texas, and I don't think that's because it's a Texas turtle that it was that much bigger. This is typical of what we find in the fossil record. Also, from the Big Bend area, we see this huge crocodile that would have been about 50 feet long, compared with a modern crocodile in the foreground. That's a big one, about almost 20 feet in the foreground, as big as they get today, but huge from the fossil record. Sharks in the fossil record were gigantic. They would dwarf jaws. Here we see the fossil of a large shark, very similar to the great white today, superimposed here on a 14-foot shark mouth. The huge shark of the fossil record obviously is just a giant. Here they are superimposed in one of the evolutionary publications. The great white today is dwarfed. A shark, you remember Jaws was supposed to be about 25 feet long. This one is at least 80 feet long and could possibly swallow a Jaws whole, or at least a couple of bites. The beaver here that we're used to seeing, just a couple of feet long perhaps, was much larger in the fossil record. Here from one of the geology textbooks, we're told that this was a beaver that was 10 feet long. I have a skull of a fossil beaver in my den. It was about 6 feet long, and the skull is gigantic. From India, we have camels that were over 20 feet tall. We have ground sloths that were at least 20 feet, and some that are recent discoveries were evidently much larger than this. This one's from the Price Museum up in Utah, and we measured the hand. It was about 18 inches. Down in Argentina just recently, they've discovered one, the hand portion. They haven't got him completely excavated. The hand portion is 3 feet long. Now, this is 18 inches. That one, 3 feet. I don't know whether the whole thing is twice as big, but it's obviously much bigger than this one. But the ground sloths we see today are maximum maybe 6 feet long. This is typical. This is what you see continually in the fossil record. Down in Texas, we have some pretty good-sized cattails. This one's almost 8 feet tall. That's a good size, relatively speaking. That's wouldn't make a Texan ashamed at all. But if you look in the fossil record, he gets ashamed pretty quick. They're over 100 feet tall. The brown portion is well over 6 feet, and this is a very common fossil, typical in the fossil record, and they're all big. We're looking here at a display from that Dakota School of Mines where we looked at the fossil pig a moment ago, and this is their sign here. They need some extra money there to help on their signs, but a quarter is put up here in the foreground for scale. This is maybe 18 inches tall, the cycad, the fern-type plant. That's the way it looks today. In the fossil record, you can't reach around it with both hands. Huge trunks, over 100 feet tall in many instances. Notice Simac's comment about the bugs in his book, Trilobite, Dinosaur and Man. He says, in general, all the Pennsylvanian insects, and that's where you find most of the insects in the swampy areas. I think it indicates environment more than age. But they were all larger. Not some of them, not even most of them. All of them were larger than the ones we know today. And I've had professors tell us when you're out finding bones, maybe in a cave, you can distinguish between the Pleistocene environments, the Ice Age, and the modern, some of the same animals, by noting that the Pleistocene are at least 20% larger. This is the way you tell it. In the past, they were bigger. Have you read that in your textbooks? You normally have to get into graduate work before they acknowledge that. We're looking here at a fossil dragonfly. Looks for all the world like the dragonflies we see floating around today. This one is exceptionally large. This has a wingspan of 48 inches. But 2 feet to 3 feet were not unusual in the fossil record, though if you saw one today, you would be really shocked, wouldn't you? Again, all the bugs, Simac said, were bigger. Now here we see dinosaur Jim Jensen beside the huge Seismosaurus leg, at least restored, a certain portion of it. And from that view, we can see this was truly a gigantic creature. These creatures are no longer on the Earth. The extinction process is not an upward process. It is degenerative, obviously. Though, interestingly, there is one remaining survivor of the beakneck family, the family that the dinosaurs belong to, on the Earth today down in New Zealand. We see the Tuatara. He's about 8 inches long. That's all that remains of the beakneck family, which is not looking like an evolutionary process. Do you get the picture here? The physical processes are going downhill. Living systems are going downhill. You can make it go uphill if you have the DNA, the information, as well as the energy. But to do it naturalistically without the information, you're just whistling in the wind. This is not going to happen. It takes more than the natural processes to get it to go uphill by itself. This law is pervasive, and I think very damaging to the evolutionary theories that says the whole universe is a unit that is overall going uphill. No, that is not the case. The most fundamental generalization science has ever been able to make about the universe says that does not work. That's just blind faith in spite of the empirical evidence. We learned in the first lecture in this series that there are laws of science and what it takes to become a law, to be proved scientifically. It takes the observation and the repeatability and the experimentation and testability or falsification. There are things that are proved, and the laws of thermodynamics are established by that criteria. And we're looking at illustrations of that which is proved and is law as opposed to theory, faith in some instances, contrary to the law, in the living systems, particularly looking at the first and the second laws of thermodynamics. In the living systems, certainly as indicated by the fossil record, things have been going downhill, contrary to what is often portrayed in the textbooks. When you know something about paleontology, you understand this is the pervasive process that is perhaps illustrative of this second law of thermodynamics. For whatever reason, it is going downhill, contrary to what the little horse charts always represent and the little men charts always No, it's not going that way. It's going in the opposite direction. When we look around us in the living systems, the world, for example, looking at the erosion here in the Grand Canyon, we're not looking at upward processes. This is not increasing, but we see a degenerative effect of the erosion, and it's happening very rapidly. We put little gizmos in the mouths of the rivers to measure both the rate of flow and the amount of sediment in the flow, and from that we can calculate the amount of sediment that's being delivered to the ocean each year. We multiply that by the volume of water being delivered by all of the rivers, and we know how much sediment is being eroded from the continents. And it's mind-boggling. There's about 127.5 billion tons per year being delivered to the oceans each year, eroded from the continents. Now, that's a figure that really doesn't relate, usually. But if we compare it to something we know something about, we can get a handle on it. If you were to fill a freight train that would reach all the way to the moon and halfway back, you could accommodate 127.5 billion tons, but it would take that much. A freight train all the way to the moon and halfway back, dumped into the ocean every year. Now, you can't just keep on doing that very long before you don't have continents. Now, we're told the continents have been here for millions of years, and many of these rocks are dated for hundreds of millions of years, but at that rate, they'd all be gone in 14 million years. Well, how do we still have these rocks that are supposed to be hundreds of millions of years old, 500 million years old, down in the Cambrian 600 million years old, but they'd all be gone in 1,400 million at the present rate. Well, things get jacked up, but still we've got this 600 million year old rock here, and that, when you average out what's across the continent according to the evolutionary assumptions, you have a real problem. It's much older than 14 million, we're told. This is a downhill deteriorative effect that is pervasive, whether we're looking at living systems or whether we're looking at the Earth or whether we're looking at the universe around us. We're looking here at a meteorite, meteor from one of the Linoid meteors. As it approached the sun, it looked like this. As it went around the sun, coming out the other side, it looked like this. It didn't get helped a whole lot by the process, and this is what we see happening. It dissipates. It comes apart. And here is one less celestial object, now evolving, if you please, but downhill, degenerating, and this is typical. We're looking here at the Ikea-Siki comet of 1965. As it approached the sun, it came out the other side in 4 pieces. Some were predicting it would crash into the sun. A beautiful sight, but it's not being helped any by what we're observing here. They degenerate. We don't see them coming into existence. In fact, explaining comets, I think, is a real challenge to the naturalist. Fred Whipple of the Smithsonian Astrophysical Observatory is writing in his book, Mystery of Comets, saying comets tend to split in pieces, particularly when they're near the sun or Jupiter, but also when they're quite undisturbed in space, and some comets just seem to tire out and die. Well, isn't this a surprise? This is what this most fundamental generalization about the universe that scientists have ever been able to make tells us, and this is what we observe. And nobody has ever observed something coming together to form a comet. They imagine some kind of reservoir out there, 150 astronomical units away, far enough away you can't look to see, and every once in a while one gets bumped out and comes into our solar system, which is just not observation, but this is theory, and that's the best origin we've got today. But what we see, what we observe over and over again, is just this. They come apart. They tend to tire out and die, as Fred Whipple has told us. When we look at our sun, we're looking at an amazing phenomenon. We're told that there are thermonuclear reactions going on here that effectively consume in quotes, about 4.5 million tons per second. Now, it's not really consumed. That first law says you can't do that. It's radiated out into space in the form of energy. But it is consuming the matter in order to radiate the energy by thermonuclear reactions. But 4.5 million tons per second by just the normal stellar processes is not helping it a whole lot. Now, it's very massive, and it'll still take a while. But in addition to those normal stellar processes, we notice there are the solar prominences and flares, and in this view we see a tremendous amount of material blasted out into space relative to the Earth, which is superimposed on this picture. We're not viewing the Earth from the sun, obviously, but superimposed to show the relative size. Just a tiny little Earth up there, a speck in the upper left-hand corner, relative to this blast of material out from the sun. What's happening to the sun? It's not getting more organized. It's being blasted out into space. It's radiating, including the solar winds and prominences, an average of about 5.5 million tons per second. It's, quote, burning up, and doing so rather dramatically. Now then, we multiply that times the billions of stars that we see in the universe, and what's the picture that we see here? Now, what we're told about is stellar evolution, and everything's going uphill. This is the faith, but the second law of thermodynamics says everything's going downhill, and that is what we observe in our star and in the other stars, which we would assume be like those that we're able to observe closely. This is a newspaper clipping I cut out several years ago. A star reported dying 8,000 light years away, here we're witnessing the death of a star, we're told. It's cooled from 30,000 degrees in 1950 to 5,000 today. This was in 1974. So about 25 years, it's gone from 30,000 down to 5,000. That's pretty dramatic in 25 years. That's what we see. I really need to replace that with a more updated version. We see those rather often. This can be observed, and sometimes we see this degeneration much more dramatically than this in the form of novas and supernovas, where a star, as illustrated in the inset here on the left, flares up to tens of thousands of times its normal brilliance on the right. One night on the left, the other night on the right. Just like a normal star, like our sun, one night, and then the next night tens of thousands of times brighter. Now then, if it's radiating something like our sun, 5.5 million tons per second, what does it do when it's 10,000 times brighter? Well, this is deterioration on a prodigious scale, and sometimes just totally blasts itself out of existence and leaves the smoke, the debris, the beautiful nebulae. And we can see these remnants. From our observations over the past 100 years, we've got a pretty good idea of how many of these supernova remnants we ought to be able to see. And we're jumping ahead somewhat to our next lesson as we talk about the age, at least of the universe. We're talking about the age of the Earth later. But we can get some calculations here based on how many of these we've been able to see. We know how many we ought to be able to see. We see the rate at which these are forming. And by the predictions based on what we observe now, in 1,000,000 years, we ought to see 7,291. There's the prediction. Now, if we've got 7,000 years, then we ought to be able to see 270 at the present rate. Now, here are two very contrasting predictions, and we ought to be able to look at the empirical evidence and see which model is served best. Well, how many supernova remnants have we been able to find? So far, we've actually observed 200. We'll probably find a few more. But which model is served best here? Which one fits the facts? We ought to see a whole lot more if the Earth, if the universe is old. Well, I'm a little off my subject, but I couldn't resist throwing that in. When we look, though, at these novas, we sometimes are also referred to areas of glowing gases, which look very similar. And here we see in a headline of USA Today, Hubble telescope captures the birth of a star. Look here, we caught this. And this is very figurative language, though not all people understand it. Because, you see, the present theory says it would take at least 100,000 years for it to actually be born, and so obviously you didn't see it happen last night. You see something in the process that leads to it, that is, your faith says this is happening, but what do you actually see, apart from this obvious assumption associated with the observation? What you actually see are glowing gases, which they assume are coming together. Now, what do glowing gases do that we know anything about? They dissipate. The expansive forces are much greater than the contractive forces, and so they spread out. But we referred to the middle star of Orion, for example, as a stellar nursery here in Discovery magazine. And these stars are becoming, these glowing gases are becoming stars. That's what they say. But now what is the actual observation? Glowing gas. Not getting brighter. It takes hundreds of millions of years. You can't see that. Does that sound familiar? It takes too long to observe that. But what we're seeing is glowing gas, which is supposed to become a star. Now, here is that middle star of the sword, the Orion Nebula, and a stellar nursery. Beautiful, glowing gas. Notice the comparison, though, with this other part of the sky. This is the Crab Nebula, and we've got glowing gas. Now, does that look somewhat similar? Here's the Orion Nebula, and then here is the Crab Nebula, glowing gas. Well, the problem in evolutionary theory of the stars is that this we know about. We know where this came from. This originated in 1054, and we have 3 recorded observations. The Chinese and the Indians and the Arabs all recorded in 1054 the giant nova, which blew the star out of existence. And this is the smoke from the explosion, if you please, the debris from a star blowing itself out of existence. Now, this one, the Orion Nebula, we really don't know where that came from. But it looks the same, like glowing gases, and so we assume it's coming together here. Now, this we know about, and we know it's coming apart. We see glowing gases, but from what we know from history, we know it's going in the opposite direction. Well, how do you get the other to contradict that second law and come together? And sometimes they say, oh, it's just gravity. Well, we know gravity acts on gases, but so do the expansive forces, the laws that say they spread out and dissipate, and they're about 60 times greater. How is 1/60th of the force going to contract? The real authorities in this field will say something very different from what you read in your textbooks, and the uninformed authorities. J.C. Branded, one of the leading authorities in astronomy today, in his book Sun and Stars, says contemporary opinion on star formation holds that the objects called protostars are formed as condensations from interstellar gas. Now, how is this gas going to condense? That's what it has to do to form a star. He said this condensation process is very difficult theoretically, and no essential theoretical understanding can be claimed. In fact, some theoretical evidence argues strongly against the possibility. Well, what is the evidence? He's talking about the second law that says it spreads out. It gets more disorganized. It's very difficult to go against that second law, but they have great faith. Oh, gravity pulls it together. Well, gravity doesn't do it with the gas that we're familiar with. And when we measure the forces, the expansive forces are much greater. Now, once you get it to a certain critical point where it is compressed, theoretically you can make it then begin to contract, but how do you get it to that point? Well, some of those trying to explain star formation have tried to wrestle with that, and they say, well, maybe you've got a couple of supernovas with some gas in the middle, and these supernovas go off at the same time and squeeze this gas in the middle, and that gets it to the critical point so it'll go on its own. That's pretty contrived. That's but you have to have stars blowing up on either side to start with. How did the first one get started? Well, you see, you've not really explained origins at all, even with this contrived explanation, certainly never observed. Abraham Loeb of the Harvard Center for Astrophysics, writing in New Scientist, and this is not a lightweight, this is one of the leading authorities in the field, says very plainly, this is 1998, the truth is we don't understand star formation at a fundamental level. Now, in your undergraduate textbook, they'll say, oh, we know all about it. Gravity does it. That's ridiculously simplistic and misleading, deceitful. Abraham Loeb of the Harvard Center for Astrophysics says we don't understand at a fundamental level because he understands the implications of these expansive forces which are stronger. Godfrey Burnbridge, who is the director of the Kitt Peak National Observatory, in his book Stellar Structure, is dealing with this issue, and he says if stars did not exist, it would be easy to prove this is what we expect because it comes about faster and with greater force. It spreads out more than it comes together, and so we wouldn't expect them to be here. They burn up quicker, and they should have burned up according to what we're observing if the Earth is, or the universe is nearly as old as he would predict. What we expect is different from what we see. But we not only see these assemblages of gases called stars, we see assemblages of stars called galaxies. How did they get organized into galaxies after getting organized into stars? With the second law saying they go the other way. Now, around the edges here of the Andromeda galaxy, there seems to be some dissipation. Now, we can't see that happening, but at least that would be consistent with our observation. It seems to be spreading out around the edges. How do you get it to hold together? Well, sometimes they invent dark matter. Nothing like any matter we've been able to see or test are subject to empirical science. And there is some empirical evidence indicating that we've got dark matter associated with the galaxies in the halo around the edges. And if it's heavy, and it needs to be to fit their theory, and it is old, it should have gravitated toward the center. If it's heavy and light, now out toward the fringes, which is where the observational indications are, then that's an argument for the young age, not an old age. And so that really doesn't help a whole lot. But notice James Treffel's observation, professor of physics at George Mason University, an often quoted authority in this field. He says it seems the more we learn about the basic laws of nature, the more those laws seem to tell us that the visible matter, the stuff we can see, shouldn't be arranged the way it is. It should have spread out and dissipated, but it is organized, and it has come together, not the way naturally the smoke from the campfire does, but the way you do it when you impose information and energy. Treffel says the basic laws of nature shouldn't be arranged the way it is, if it's as old as they're saying it is. He says there shouldn't be galaxies out there at all. How do you get this organized bunch of gases to organize themselves? Even if there are galaxies, they shouldn't be grouped together the way they are. Not only shouldn't there be galaxies, there shouldn't be groups of galaxies. This is the third level of organization that we observe, that by natural law, by natural processes, shouldn't be there, which the authorities will acknowledge. Bruce Morgan of University of Washington says it's a fairly embarrassing thing for the astronomer to admit we can't find 90% of the mass of the universe. In order to hold it together, you need a whole lot more mass. You need 90% more than what you've got. That is, for a long period of time. It's a constant, ongoing scandal. And so they come up with this imaginary stuff called dark matter, and there's serious, serious problems with that. Many are giving up on it. Trefel says the problem of explaining the existence of galaxies has proved to be one of the thorniest in cosmology. By all rights, they just shouldn't be there, yet there they sit. Does this sound familiar? Like the stars. It'd be easier to explain if they didn't exist. Well, the same thing's true of the galaxies. They shouldn't be there according not to Sunday school lessons, but the physical laws of the universe that we can test and observe. Martin Rees, a famous astrophysicist, was quoted in the Dallas Morning News several years ago, saying the most basic questions about galaxies are still not understood. In fact, if galaxies didn't exist, we'd have no problem explaining that fact. Well, you almost feel sorry for them. But this is exactly what the creationists would expect. Things are going downhill. And if they've been there for billions of years, they shouldn't be there. But they are, and there is great difficulty when you have an honest expert dealing with all of the evidence trying to explain this. Sir H. Jeffreys of Cambridge is talking about the solar system a number of years ago. He says, at that stage of the game, I think all suggested accounts of the origin of the solar system are subject to serious objections. The conclusion in the present state of the subject would be the system cannot exist. Well, that was the case with stars, and that was the case with galaxies. That's the case with groups of galaxies. And of course, there are much larger systems, the great walls that we found now that defy explanation in terms of the years, that even the great years that are proposed for the universe. But now with the solar system, he says, The present state would be, the conclusion would be they can't exist. Well, that was 1970. Maybe since then we have seen some progress. Let's see what Fred Whipple has to say. He says all of the hypotheses so far have failed or remain unproved when the physical theory is properly applied. He's talking about the solar system in his book, Orbiting the Sun. Now, the difficulties involved here well, we'll talk about more of those difficulties in a moment, just to illustrate. But he sees problems and they have all failed. Well, this is 1981. And then we move forward to an article in Nature. This is 1997. And we're told many models have been proposed for the formation of the moon, but no one has succeeded in showing the formation satisfactorily. It can't be made to work in terms of natural laws. To illustrate just a few of those laws, we see in the solar system that the sun has 99% of the mass, whereas we see 99% of the angular momentum in the planets. Now, how did 99% of the angular momentum get transferred from 99% of the mass to this 1% of the mass? I just defy you to explain that, and they can't. They just say, wow, I don't know how that happened. We have a slow spinning 99% of the mass, which is supposed to be the origin of, would be talking about most of what's there, 99% of the mass, but these planets have a rapid orbital motion. We see some of the moons spinning one way, we see some of the moons spinning the opposite direction. We see retrograde motions throughout the planetary cycles that are all supposed to condense from the same cloud. This does not fit, which is why the experts again and again say it shouldn't be there. We shouldn't be seeing what we're seeing. I think it was created in order to aggravate those who try to explain it naturally. Stuart Ross of the Lunar and Planetary Institute recently says the ultimate origin of the solar system's angular momentum remains obscure. You cannot explain it by planetary physics. It doesn't work that way. Going back to Asimov again, summarizing the overall picture, he says, as far as we know, all changes, and that's whether you're talking about the physical systems, machinery, or whether you're talking about the living systems, or whether you're talking about the continents eroding, or whether you're talking about the comets, or the meteors, or the sun, or the billions of suns, or the galaxies, whatever you look at, what you see, he says, as far as we know, all things are in the direction of increasing entropy, or of increasing disorder, of increasing randomness, of running down. Now that's everything we see, and it's been that way for as long as we've been seeing. But then he makes an interesting observation. Yet, the universe was once in a position from which it could run down for trillions of years, he says. He asked the obvious question. He goes on to say why before we go to Lipsom's statement. He says things were much higher. How did it get in that position? How did it get there? Well, it didn't get there naturally, because natural law, the most fundamental generalization scientists have ever been able to make about the universe, as Einstein says, the one in which I've got most confidence, says it goes the other way. How did it get up so it could run down? Now, what does Asimov say? He says nobody knows. Like he said before, it's just a big why, and nobody knows why. Well, let's just be honest about it. By physical law, by natural processes, it's not going to happen. What does that tell us? It did happen. Not by natural processes would be a very reasonable conclusion. You don't directly observe that, but what we do observe fits the model directly as a prediction of that model. There are some physicists who will face the implications here. H.J. Lipsom is an atheist. But he says, I think, however, we should go further than this, talking about the implications of the second law, and admit that the only accepted explanation is creation. Everything we see is going downhill. How did it get up? Well, you don't do it by the laws that we see operating now. You have to have supernatural laws, and that's what he says. He continues saying, I know that is anathema to physicists, as it is to me. I would say some physicists. I think the better ones don't see physical observations as anathema. They love the truth, the facts, the evidence. But he says, it is to me, and we must not reject a theory that we do not like if the experimental evidence supports it. The explanation, the best one, is supernatural. Because this is not Sunday school material that supports it. This is not a religious investigation. This is the experimental evidence that supports it, according to the atheist. How do you explain the origins of things in the universe? Well, you can't do it his way. You have to do it our way, if you please. And two very brave men make a statement with which we'll conclude this lesson. The book Fundamentals of Classical Thermodynamics is taught as a textbook in thermodynamics in universities throughout the country. It's in every state university in Texas. This is the standard textbook. And they make this very brave statement, and I think very obvious statement. We see the second law of thermodynamics as a description of the prior and continuing work of a creator. who holds the answer to our future destiny and to that of the universe. And why would they say that in the face of the overwhelming opposition of the establishment? That's because that's what the physical evidence tells us. There's no other way to explain what we see with regard to these laws, which are genuine laws that fly in the face of many of the theories, the philosophies, the faith of the naturalist. But the naturalism has not been established by science, and there's no reason to call that science. Let's just look at the physical evidence and see which fits what we observe best, and that should be the most scientific. And it's not the naturalistic view that can explain what we see in the universe. It takes something else, and these brave men tell us exactly what it looks like. As we saw in the living systems, even Crick says it looks like a miracle, and when we look at the universe around us, it looks like the work of a creator, as well as the physical systems everywhere we look. I think that's the best explanation of origins. As we compare the two models, one is superior, and I think it's obvious which.